All right, this is Kurt Schmidt. I'm doing a quick summary of Tuesday, September 8th's lesson for those of you who need a review or who missed the Zoom session. That's just a recap of the Zoom session for today. All right, so what we're looking at here is going over our lab expectations. Hopefully you've done part one of the ball drop lab and you have your data. Ideally, you have your conclusion as well. That's not due till tomorrow, so I know some of you are still working on that. We'll then talk about what should be in the discussion and your improvements and assignment going into tomorrow. Okay, also notice that later this week we're going to have another storm time session around getting involved in the handbook. Those are required. And then Friday we'll start talking about velocity. For those of you wondering, I'm in my office today because the power was out. I expect a few other people might also be under the same shape. Power, internet might have been interrupted today. I hope you're all doing well and safe. My understanding is power is coming back on across town after the windstorm last night. So let's talk about lab expectations. So when I look at what I want from a lab, I go to this kind of document in terms of what does a full lab look like. This is not going to be our exact grading rubric, but if you're going through a checklist of what you should do and how it should look, this is a great thorough listing of everything that should be in a proper AP lab. Okay, so I'm going to come back to some of these elements in our actual rubric here in a minute in terms of grading. Okay, it's important to note that for part one of the lab, our first ball drop lab, I did not publish a rubric. I'm just looking at you've attempted every element and that we have something to start a discussion on. So the rubric that we discuss here today will be for part two. Okay, one of the biggest problems we have in the ball drop lab is parallax. Okay, parallax is a well-known problem, or actually it's a tool used sometimes in astronomy where you can compare a planet or an asteroid or a comet to the background stars, and based on where you are in June and where Earth is in January, we can use that movement of the Earth across space to triangulate a point for where that other object is versus background stars. Okay, we're not trying to deal with astronomy and finding points based on motion of the Earth and background stars. We're trying to take an accurate measurement of a ball being dropped. So how do we do that? What our problem is can be exemplified if we hold up our finger and we look at with one eye and then we look with the other eye. It looks like the finger has moved versus the background. Now, if that is your ball falling and your camera is at one angle versus your camera is at a different angle, that's going to show a different mark on the background, on where the wall measurements are. And so where your camera is going to affect the parallax. So hopefully based on your hypothesis, if you said it's going to return to a 75% bounce rate, then that's where you should fix your camera. So it comes up and you get a perpendicular image against the markings on your wall. And then when you set your next drop, move your camera down again. So if you're dropping it from a lower height, you expect a lower return, and you still get another perpendicular marking to avoid that parallax error. Okay, so that's one of the things you might want to think about in your conclusion, and you might want to put your proposal for part two. Okay, because what we're looking at here is we're still trying to plan and conduct scientific investigations. We're now trying to fine-tune it and improve it based on the first attempt we did on our lab, where we're now going to conduct and analyze basically a similar lab using what we've just learned about lab technique from part one. Okay, so procedures should look very similar. You're just going to add one more piece, and notice that in my diagram, we have things labeled, okay? It's typed or very clearly written. It's gonna be something we're gonna want to see in your part 2 of your lab. All right, so we're still trying to predict the drop heights. And this time when you do your hypothesis, I expect a much more accurate hypothesis because you have all this experience from part 1 where you used a ball, you used the same floor, you should have a much more accurate prediction. But we're still doing everything in meters. We're still doing the if, then, because. It's just now your because statement should be more thorough and more insightful based on part 1. So what we really want to do is focus on your part 1 conclusion, where you said, how are you going to use technology? You get a brief proposal, and you said, how are you going to implement those changes with the materials you have available? Okay, if you said you're going to do something based on the materials you had available and those are not available, then we have a problem there, okay, because I'm going to expect you to follow through with those proposals. Okay, so people have a number of different things that I've been commenting on as they came into Canvas. Almost half of you have turned it in by the time of this recording. So really follow your Canvas comments based on what your proposal is and what my feedback is from your writing. Okay, so that was your conclusion for part 1. Again, it'll be your conclusion for part 2, only the new thing is include changes to your procedure. Okay, so now you said, oh, I had this problem. Like every time I tried it, my little brother bumped my elbow. So I'm going to lock my little brother out of the room. I don't know what whatever your thing was that was causing variation within your data. We want to try to tighten that and use it better. Okay, so if we look at the assignment, we'll see that I have a much more detailed rubric for part 2. So this is not going to be used for part 1, the one that's due tomorrow, but the rubric in the lab will be for part 2, where you do a similar process, only now we really want you to focus on precision, okay, and accurately reporting it in a full lab report. Okay, so as we go through these, your introduction, all right, you're going to present a clear and accurate and complete research. So maybe you talk a little bit about your last lab and information that carries over. Okay, then you have your variables, which is going to feed into your hypothesis. So you're dropping the ball from a set height, that's your independent. You're measuring the return bounce, that's your dependent. And then you're trying to control for camera angle and type of ball and type of floor, and anything else you're trying to make sure doesn't change will fall within your controls. Okay, and all this is clearly and accurately reported. Okay, and that gets us back into our hypothesis, which should be an if then because statement. Okay, and once again, your because should be much more precise and reflect on some of that stuff you learned from part 1. Okay, now notice your lab report is not a diary or not a murder mystery or any type of English literature. It is a very precise, detailed reporting of what happened. So you don't say, I dropped the ball. You'll say the ball was dropped from this height. The idea being that anyone around the world can follow your procedure, okay? And they don't have to be you to get this done, okay? It doesn't make for the most exciting reading, but it means that people can quickly scan through a lab report and see what they need to know, okay? So you're not going to use any personal pronouns or talk about the people in the room unless for some reason that person affects the experiment. Okay, so when you come to your procedure, make sure it's correctly formatted, meaning a numbered list. Okay, it's clear and accurate and contains all the key details. Now, things that do not need to be in the procedure are like, I wrote down the procedure, I wrote down the hypothesis, I gathered materials. Those can all be skipped. You can just jump straight into, okay, I'll see the diagram in the materials list.
Attention staff, don't forget the Storm Express is open if you need a quick fix.
Okay, now that feels like a real school day with interruptions and announcements. All right, so the procedure is detailed, and you start right with the actual actions of the lab. Okay, your diagram, that's probably the one I could see the most improvement on. It needs to be clear and easy to understand. Everything needs to be neatly labeled. Hopefully you'll be able to put things into Kami or Google Docs, and you can type up things into a text box and drop that next to your diagram. Most published research uses graphs or like images. I say just take a photograph, okay? If you take a picture and you put in little text boxes labeling everything, labeling sizes, labeling locations, labeling objects, that will be useful. A diagram is not just a picture of a tennis ball, okay? I know that if your materials listing says tennis ball, I don't need a picture of a tennis ball. I need a picture, tennis ball is here against these things. Okay, that now you can say tennis ball, masking tape, 10-centimeter gaps, and go down the list telling me everything that what's happening neatly and accurately. Okay, so the graphs and tables, okay, again, everything is present and labeled, and it's neat, and that should be all that needs to be said for that. I will say, if you're using like video physics, that often has a great graph in it already, which saves you the work of having to type it into Google Sheets. You just screenshot it, drop it into your Google document, okay, or your Word document, wherever you're doing this on. Okay, so analysis talks about data, but does not try to explain data. It just says what is. Okay, which, by the way, it's an important point to mark that you are not, I'm always interested in people who say they don't believe science. Well, hopefully science doesn't present anything that's subject to belief. It says, here's data, here's a theory that best explains the data. If you show me different data that disproves this theory, then we have to change the theory, okay? But if all data or the vast majority of data is all explained in one way, okay, then that's going to be the theory we work with, okay? If every time I drop a ball, it falls at 9.8 meters per second squared, the theory of gravity is upheld. And if I do that 10,000 times and every time it goes forward, then that's a pretty good solution. If I let go of a balloon and it floats up, okay, now we have to expand our theory as to what else is there. There are particles in the air that are more dense than the balloon. Okay, now we start adding nuance, we start adding details. Okay, but our analysis is only, oh, we had data. This is the equations and the graphs that fall out of the data and are used. Okay, and then we have a conclusion that can use explanations and tie it back to theory. So we had a theory which gave us a hypothesis, and now our conclusion says, oh, that's our hypothesis and that's the theory. Did our data support that? Okay, was our hypothesis wrong? And then where do we go from there? Okay, if you did anything, I saw someone looked up what the tennis organizations require for a ball in competition play. Okay, they had some great research, so they had a very accurate hypothesis, so their error analysis errors was very small. If you just looked at a ball and said 50%, well, then you didn't do much research, and your hypothesis might be wrong because you really didn't have a theory you're trying to prove. Okay, so that brings us back to where I had before. You were trying to cover these points. Remember, these are the ones for part 2 that will specifically be graded, okay? Which means your part 1, if it's not already done, needs to be wrapped up and turned in tomorrow, okay? Part 2, hopefully I give you a lot of time in class. You should be able to take an hour and be able to do part 2 based on what you wrote in part 1 and what I wrote in the Canvas comments, Okay, and then that should set us up for the next class, which will be on velocity and acceleration. Okay, and with that, I hope all of you have a good day, and I'll see you later.